This is a member of Naegleria Fowleri, also known as a brain-eating amoeba. Let's call them Bia. Bia likes to hang out in warm fresh water, and when the conditions are favorable and there is plenty of food, they are in their trophozoid stage, also known as the amoeboid stage. If temperatures drop, or if it becomes overcrowded, there is too much waste, or if they are dehydrated, Bia will protect themselves by transforming into a cyst. In this stage, they are spherical with a smooth single layer and are 7 to 12 micrometers in diameter. Cysts are often clumped closely together, and on average, each cyst has 1 to 2 mucoid plugged pores. Whilst they are a cyst, Bia is dormant, they cannot eat or reproduce. But when conditions become favorable again, the Bia's trophozoid form will emerge from one of the pores. If conditions are favorable but food is scarce, Bia will transition to their flagellate stage. They cannot eat or reproduce in this stage either, nor can they transition into a cyst, but it allows long-distance movement to pursue food. In this stage, Bia has an elongated, pear-shaped body with their nucleus in the narrower anterior region. They have no cytostome, but they have a distinct nuclear membrane and nucleolus, vacuoles and cytoplasmic inclusion, mitochondria and rough endoplasmic reticulum. They also have 2 flagella of equal length which they use for movement, along with the associated kinetosomes, rhizoplast, and fin-walled fibrils. Once food has been found, Bia will transition back to the trophozoid stage.
But things are about to take a dark turn. Bob, unaware of what's lurking in the water, dives headfirst, and with that splash, Bia rides a wave of warm, fresh water straight into Bob's nose. Once inside, Bia doesn't waste any time. They attach to the olfactory epithelium, the thin layer at the top of the nasal cavity. To get to their destination, they cleverly disrupt the proteins that hold cells together, slipping through tiny cracks and making their way past the cribriform plate. And just like that, Bia is in the brain. But how does Bia manage this so easily without getting caught by Bob's immune system? At first, they fly under the radar. In the early hours after infection, Bia settles into nasal mucus undetected. Secretory antibodies like IgA and IgM are there, but they don't seem to stop her. Even immune cells that show up early can't eliminate her. Bia doesn't trigger alarms, no epithelial cell death, no inflammation. This stealthy move lets her access Bob's olfactory neurons, hitching her right into the central nervous system, bypassing all the usual defenses. Once Bia reaches the brain, the real damage begins. Bia begins destroying tissue fast. She eats live neurons through a process called phagocytosis. She releases destructive enzymes like phospholipase A2, cysteine proteases, as well as amoeba pores that poke holes in cells. Bia even sends out toxic vesicles that mess with calcium balance and generates deadly oxidative stress. All of this causes the brain to swell, bleed, and break down before Bob's immune system can even catch up. When the immune cells do arrive, it's already late. The brain's microglia and astrocytes recognize the invader and go into overdrive. Cytokines like IL-1, TNF-alpha, and IL-6 flood the brain, calling in neutrophils and monocytes for help. But while they try to fight off Bia, they also cause collateral damage, more inflammation, more pressure, and more destruction. This is how Bia, a microscopic amoeba from a quiet lake, turns a swim into a medical emergency.
Bob is brought to the hospital because his symptoms are getting worse, indicating something more serious is going on. After a lot of tests to figure out what is wrong, a spinal tap is performed to see if Naegleria Fowleri is in the cerebrospinal fluid, as well as a brain biopsy. For the biopsy, a tissue sample is taken and examined to check for the presence of the organism under a microscope. To the shock of his doctors, Bob is found to have PAM. As you probably know by now, This is a very rare disease, so not a lot of research has been done on the right course of treatment. Current knowledge about potential therapies is largely based on isolated case reports and experimental data from laboratory and animal studies. However, the scarcity of cases and the disease's swift progression make it extremely difficult to conduct clinical trials to assess the safety and efficacy of these treatments. An aggressive course of treatment is decided upon due to the very low prognosis. Did you know? The fatality rate from the infection is 97%. Amphotericin B has become the primary drug of choice for treating primary amoebic meningoencephalitis, PAM. Its use is associated with multiple side effects due to its lack of aqueous solubility. He is put on combination therapy, meaning he will be put on different medication on top of amphotericin B, in the hope that it will delay the propagation of the infection and preserve brain tissue to give more time to the drug to take effect. He is also put through hypothermia therapy. If this works, he might be left with brain damage and or have to take the medication for a few weeks to a few months. And if it doesn't, he will go into a coma and will then die. Bob's parents are naturally wondering, why was there no sign in order to warn there was a danger? And they will be right. However, putting signage is not recommended for 3 simple reasons. First of all, the location and a number of amoebas can vary over time within the same body of water. Secondly, there is no standardized testing methods to detect and determine the number of amoeba in the water. And finally, it could lead people to mistakenly think that a body of water that does not have a sign is free of Naegleria Fowleri. So, what can we do? Unfortunately, there is no guaranteed way to make fresh water completely safe. Right now, prevention is the best defense. That means avoiding warm, untreated fresh water during hot weather. Don't force water up your nose. Use sterile saline for rinsing. Wear nose clips if swimming or diving in warm lakes or hot springs. And no, PAM cannot be caught from swallowing water with Naegleria Fowleri. It enters through the nose, not the mouth. It's also not found in salt water or properly chlorinated pools. But what about the future? Researchers around the world are racing to outspace BIA. There is sequencing Naegleria Fowleri's genome to uncover its vulnerabilities and understand how it invades and damages the brain. They are investigating the parasite surface proteins and virulence vector, hoping to find weak points that could be targeted by drugs or vaccines. Some labs are testing experimental treatments in animal models, not just new drugs, but novel delivery methods to get therapies across the blood-brain barrier more effectively. And while there is no human vaccine yet, preliminary vaccine trials in mice have shown real promise. In some cases, vaccinated animals survived what would otherwise be a lethal infection, a small but hopeful step forward. Still, progress is slow. Funding for rare diseases is limited and Naegleria Fowleri infections remain uncommon, but every insight counts. Filling the gaps in our understanding, how the amoeba spreads, how it evades immunity, how it kills, could lay the groundwork for faster diagnostics, better treatments, and, eventually, prevention strategies that go beyond personal risk reductions. For now, BIA is still rare, but deadly.